Okay, we still have 4 minutes, so please wait for a few minutes.
有，我也是修很多。修很多修考试的课程。
那肯定进入比较写1张的，让他每次都给2张。3个下就各1张。
摄影是谁？
老师，光谱就是如果你有收到可能记录下一个环节的话，我们就直接把时间切进去，就不会再等到它上台以后才来。
要听我的指示还是你们会自己判断？
我们会自己判断，有老师就这样子。
Oh, okay. Okay, now it's 8:30, so let's start this slide. At first, let Jules introduce ourselves. I'm Zheng Xiande, coming from Donghua University. And please, Jules, introduce yourself.
I'm Fan Chen from National Tsinghua University and the National Central University.
National Central University.
台湾大学物理系蔡尚芳。
Dear professor and students, good morning. Good morning, everyone.
Good morning.
My name is Xianglin Lu. I'm from Department of Physics, National Taiwan Normal University. I enjoy reading, jogging, and swimming. Thank you very much.
Okay, then please each team introduce yourself and your members. The first here.
Good morning. We're me too from Taipei Senior Weigo High School. And I'm Yu Dongyue. This is Lin Muyun. This is Wang Lian. This is Wang Xuanqi and Liao Zeyu. Thank you.
大家好 we are all girls from Qingxin Academy. 我是许长熙，这是杨尚武，这是李正燕，这是黄玉红，这是张佑丹。
I'm the captain from Team Excelsior, and I'm Chen Yuqian. She is Lin Yixuan. He is Lin Kaiwen. He is Zheng Yuchen. He is Hou Chenshao. Thank you.
I believe every team already well known the old rules. So let's begin this stage. Okay, at first, opponent challenges the reporter for the problem.
We'd like to challenge problem 8, another magnetic levitation.
We would like to reject this challenge.
Okay, reject.
We would like to challenge problem 13, charge meter.
Who would like to reject the charge?
Okay, GJ. Okay, problem 5 is open.
We'd like to challenge problem 5, ping pong rocket.
We would like to accept the charge.
Okay, so we have 5 minutes to repair.
第4个，第3个。
Hello, juries and fellow competitors. I'm the reporter from Team Excelsior, and today I'm going to report problem 5, ping pong rocket. Here's a problem statement. We put the ball in the center of the ping pong ball, and we drop the container. And the ping pong ball will get launched to the very great height. And what maximum height can you reach it up to 2 meters of water? And we'll mainly focus on the mechanism of this phenomenon, how different parameters affect the maximum height. And this is an outline. First, we'll talk about the preliminaries. And we'll talk about setup and observation. And next is explanation for why displacement was in the jet and quantity. And after that, we'll talk about the measurements and analysis for constant measuring, drop height, and water mass. And next is discussion, and after that, we'll talk about conclusion. And first is preliminaries. And this is our setup. We use the string to connect the bucket. And we use the aluminum extrusion to build the structure. And we put the boarding under the aluminum extrusion. And in order to keep the ping pong ball in the center of the container, we use the iron wire to keep it. And two fixed blades are put on two sides of the aluminum extrusion. And this is an observation you see at the video. And you can see the ping pong ball will lift to a very great height. And this is the T chart of the ping pong ball. And the displacement in the x-axis is very small, so that it can be ignored. And this is the Y chart. First is the free fall state where the container hit the ground before the collision, and after collapse, it will reach to the maximum height. And this is an observation for the jet. And water will undergo the following process. First is the container collects to the ground, and after that, the wet from the bottom of the container will gather into the position of the ping pong ball. After that, the water engine jet will form and lift up the ball. And this is the explanation. First is quantitative explanation for wet displacement. First is the free fall stage, and the ball falls along with the bucket with gravity. And after that, after collapse, it's the rebounding stage. And due to the water engine jet and the momentum transfer to the ball will be rebound to greater height. And this is a water engine jet. When you look at the video, under the ping pong ball, there's a huge jet which under the ping pong ball. And we think when the container is dropped, the gravity of the ping pong ball and the buoyancy force are not act on the mechanism. And the ping pong ball are only act by the capillary force, and the alternative or dominant force from the mass of the ping pong ball and the buoyancy force to the capillary force will cause the vacancy, and which is located in the position of the ping pong ball. And this will also generate the velocity field, which exactly is the water engine jet. And it explains the result about water engine jet. And it means that the water engine jet is a main effect of the phenomenon. And this is the theory for momentum transfer mechanism. And in the free fall state, the capillary force takes place, causing the mass of water displaced by the ball increase, and this occupies the vacancy space. And then we can calculate the water mass displayed by ping pong ball as this equation. And when the container hits the ground, and the gravitational force takes place, and the velocity field will generate and create a huge jet and transfer the momentum and to the ping pong ball. And this is the theory for momentum conservation. And first we present U is the velocity of the ping pong ball before collision. And we use the momentum conservation to calculate the initial velocity of the ping pong ball. And that we assert that when the container is dropped to the ground, the water out of the cross-section area of the ball almost remains static. And so we consider to use the continuous equation to calculate the jet velocity. And the rebounding height of container is related to water volume is developed. And we can calculate the final initial velocity at this equation. And next is we consider error resistance into this balloon. And first, we consider the error resistance is proportional to the velocity, and we use to the motion to create a sentence and we integrate it, and we can lead to the time that the ping pong ball reaches the maximum height, and the functional v that depicts velocity with time. And this is the theory for maximum height. We integrate the function of v, and we can lead to the y maximum, which is the maximum height of the ping pong ball. And this is the measurement and analysis of measurements for a cylinder. And we can see we measure the rebounding height of the container, and we assume that the moment that the collision that the water velocity is equal to the rebounded velocity of the container, and we assume the coefficient of the restitution to be taken to the water mass, and we found that the water mass increase, the coefficient of restitution will also increase too. And next is the change in depth of the ping pong ball. In theory, we assume that theta is constant, and we will find that. So this is the time, the release height, and the changing depth of ping pong ball. That the ping pong ball will sink into the water by the conveyor force, and the time scale of dropping is small enough so that the absolutely remain constant. And this is the changing theta of the ping pong ball, and this ping pong ball is also remains constant too. And this is the relevant parameters. First is drop height, and next is the water volume from 0.5 to 2 kilograms. And this is the first picture for drop height. As you can see, when the drop height increase, the revolving height will increase too. And this because when the drop height increase, the potential energy convertible to the kinetic energy will also become greater. And next is the mass of the water. And when the water increase, the revolving height will increase too. And due to the conservation of momentum, when the mass of water increase, the revolving height will increase and the cylinder will increase too. And this is the discussion first for container radius. And this is the container radius for the rebounding height. And as you can see, when the container radius is increased, the rebounding height will increase too. And this when the radius of a container increase due to the continuous function that we mentioned earlier, that the rebounding height, rebounding velocity, jet velocity will also increase. And this theory isn't fit our experience in some situations, so that we want to discuss this in next part. And for this part, we want to discuss the shock wave between the edge of the bottom. That during collision, the shock wave from the bottom to the position of the ping pong ball, and from the edge to shock wave from the edge to the position of the ping pong ball. That we want to discuss this, and we assume the shock wave is travel in liquid are so 50 to 1. And third, we have the wave velocity as this. And due to collision, there will generate two directions of the T2 wave, which I mentioned there is the wave from the bottom and the wave from the edge. And we can calculate the time of the X displacement and the time of Y displacement. And the time individual wave from two directions reach to the ping pong. And next is also the distance issue. And when the time of X displacement is close to the time of the Y displacement, and it can have the maximum height, maximum jet. If the two directions of wave vary into the ping pong ball at the same time, the maximum jet will happen. And this is a computation usage from the second equation, and we minus this to this, and we can reach to this. And when this equation approach to real, 0, and it has the best efficiency of using shockwave. And this is discussing for continuous radius and interval distance different due to the radius. And as you can see, as the delta approaches to 0, the maximum height will happen based on the concept of efficiency of using shockwave. And this is for volumes of water can reach the maximum height continuous radius. And this is discussion for continuous radius. As you can see, at the continuous radius 8 centimeters, and it can reach to maximum height, which is fixed to we mentioned earlier that the ACM can reach the maximum height, and this is the theoretical predict that it's about 7.5 centimeter, and it's mentioned the importance of the shockwave. And next is position of the ball, and as you can see, when the position of the ball from the center of the container to the middle of the ping pong ball, and when the position of the ball increase, the rebounding height will decrease, and this is because the energy loss from the shock wave. And conclusion, first is what maximum height can reach that 2 liters of water, and when the release height increases, the rebounding height will increase too, and in 2 liters of water can reach to the maximum height, and when the ping pong ball's radius is about 8 centimeters, it can reach the maximum height. As the delta approach to 0, height will happen. And next is the mechanism of phenomena. And this is when the drop height increases, the rebounding height will increase.
Hands up. Okay, opponent.
So first of all, I would like to ask, how do you change the position of the ping pong ball?
We use iron wire to change it, and we measure the ball center of the ball, and from the distance from the center of the container to the center of the ball.
So do the ball have contact with the iron container?
It may have the contact, but we have done experiments for several times, so that we can make sure that the rebounding height won't be quite different.
So do you notice that when the ball is in contact with the metal thing you keep the ball, there will be a frictional force?
It will rebound in different way, right? I think the effect of iron wire is less than if you don't use the iron wire, it will fall to the side of the container, and I think it will affect more than the rebounding height as well in different angle, rebounding different angle. Yeah.
Thank you. And I would also like to ask about the shock wave. You only calculated the shock wave from the middle bottom part of the container and the top part. What about from all sides of the container? They might even cancel out.
In our experiment, the container we use, the side is vertical to the ground of the bottom of the container, so that we think the wave is only.
Okay. Opponent. Okay. Well.
Hello, I'm the opponent of Team U2, and now I'll be proposing problem 5 in ping pong racket. So, first let's start with the problem statement. It says that a ping pong ball is placed in a container of water. When a container is dropped, the ping pong ball will get launched to a great height, where maximum height can be reached up to 2 liters of water. And the reporter's main focus is the mechanism of this phenomenon and discussing the different parameters. So their phenomenon is that when they drop the container, the ping pong ball will get launched to a great height. And their theory is about the y displacement, which is free fall and rebound, and Worthington jet. The force caused by the force has something to do with vacancy space and velocity field. And then the momentum transfer mechanism, momentum conservation, and air resistance, which is about the drag proportional to velocity. And their experiment setup includes stream, bucket, launching platform, fixed point. And they also did the rebounding height of the container, changing depth of the ball, changing theta of the ball, the drop height, and the mass of the water. So first, their pros. They have clear explanation and observation of the phenomenon, and they consider different factors in their theory, including air drag. And they did the experiment several times. However, they have vague description for the data, and they have unclear graphs and charts with no error bars. So next in my discussion, I'll be discussing the theories, including the conservation of energy, surface area, and wave direction. And the phenomenon I'll be talking about include the relevant parameters affecting the maximum height, and the others are the container direction and the ball step into the water. And now I would like to invite the reporter on stage. So, could you turn the page to the GIF where you dropped the container? Yes. So, you mentioned that with Worthington jet, the ball actually had to sink into the water, not completely, but there will be an air capsule under the water. Correct? So, have you observed the air capsule under the ball in your observation?
Air capsule.
Yes.
In my observation.
Yes. Your experiment.
We think the ping pong balls he think because converter force, and he will make the pressure difference when he hit the ground. He will have the pressure difference from the ping pong ball.
But what I'm asking is that, so you're using the Worthington jet theory, right?
Yeah.
But have you actually observed the air capsule under the ping pong ball for you to use the theory?
No air capsule, but the vacant space that generates the ping pong. No capsule, but the vacant space there.
Oh, yes. So you did observe it in your observation?
We have observed the vacant space that referred by ping pong ball, by the force. Yeah.
So next, I want to ask about your graphs. So you mentioned that you did the experiment several times to delete the errors. But however, I don't see error bars in your.
You mean that there's a error bar, yeah, and in some parts that error bar is very small. So so it didn't show on the graph.
So what you're saying is that
There have the error bar.
So what you're saying is that the position of the ball is almost always in the middle, so that the container doesn't the position of the ball doesn't really affect the exterior.
I think the main effect of the error bars is because the position of the ping pong ball, that it will have the energy loss that will let the ping pong ball
Yes,
rebound
and
in
in
different
the
heights.
graph you said that the error bar is so small that we can't see it. So this basically means that your ping pong ball is always in the middle, that it doesn't touch the exact before it. So there's almost zero energy loss.
I didn't mention it's zero energy loss. I just we just mentioned that it doesn't have a very large impact.
Okay. Now could you turn to page 28? So what I would like to ask is the position and the shock wave of the ball. So you mentioned that the shock waves are from the edge of the container, but you only calculated the top and the bottom.
Yeah.
So do you notice that shock wave comes from all directions from in the container?
In our instrument, we use the container we use is vertical, vertical to bottom. So I think the shock wave it will create a negative correlation. Yes. The shock wave only affects like here and the bottom of the vertical motion.
So you don't think that the shock wave will move like this?
I don't think so.
So you notice that, so with this container you use, the shock wave only moves vertically and horizontally. Is this what you're saying?
I'm not saying, but I believe that the shock wave, we use the motion and all the wave that will gather to the central position of the ping.
Yes, all the shock waves will move to the center of the ping pong, including shock waves from the whole container, like this. Or how do you think the shock wave from here will move if it doesn't go to the middle?
I think this is just like the.
So you think the shock waves from this side will all move horizontally? Is this what you're saying?
But I think the main effect of the shock wave is from bottom and the side of edge of the.
Okay, so have you calculated the speed of the shock wave? I mean from the bottom.
Bottom and the speed shock wave is the rebound angle of the.
I'm asking this because if the ball is launched before the shock wave from the bottom could even reach it, then it doesn't have an effect on the ball. So have you put this fact into consideration when calculating the effect of the shock wave?
Effect of
So you mentioned that you think the bottom shock wave has the most effect on the launch ball. Is that correct?
Yeah.
And have you?
Also, that's really.
Yes. Have you calculated the speed of the shock wave that before all the other shock waves reach the ball at the ball launch? Do you think the speed of this shock wave can travel to the ball before it launches?
Before it launches. I mentioned in the discussion part. Like the time gap between the edge of the ping pong ball and under the but the time gap from the edge of ping pong ball to the
Okay.
the
So you still don't consider the other waves from the side, right?
yeah, I think this is
Okay. Can you turn to your setup page? So I would like to know, how do you know that the container always drops vertically? Like it would always have some tilt, right?
You mean the connect angle?
Yes, the contact angle to the ground.
We have some graph that we observe that when the connect angle increases, the rebounding height will decrease, and I think this is because they might have the two collapse between the body, so that the energy transfer to the ball will be dispersion, so that the rebounding height of the ping pong ball can really let launch to a very great height.
Okay. So have you? So is your container straight? Like in the picture you draw, the side of the container is straight. However, in this graph, it's tilted.
This is I just want to show the connect angle, and this is just this is not the.
Okay, thank you. But it's an important question because the shape of the container affects the waves that the distance of the wave from the ball. So I want to make sure that your container is as strong as the board or on the side. Is it straight or?
Yes, straight. It's
Can we see your GIF again?
Like this, we use the straight one to do that too.
Well, in the question, it says that what is maximum height you can reach with 2 liters of water? So have you? So in this picture you have, I don't think the water is 2 liters. Have you ever conducted an experiment with 2 liters of water?
2 liters. Yes, I have conducted that, and I have this.
Do you have video or pictures of you using?
Pictures. I didn't put in this report, but I have a graph that shows the evolution. Then we observe when the radius is 8 centimeters.
Okay. Well, so when the radius of the container is 8 centimeters, that's below the normal. So, do you think the shape of the container would affect?
I think
Do you think the top part of the container, the 8 centimeter radius, are you talking about the top part of the body parts of the
it's vertical, and
yes.
I think if you use this one, that might affect the result. When we use this one, according to our theory, we use the linear equation so that the wave can go into the energy can transfer to the human ball.
So the 8 centimeters is the bottom of the So your theory can only be used on a container that has the same radius throughout its height, right?
Yes, we just measure the vertical.
So, well, I think you can conduct more experiments maybe on the shape of the container so that your theory can be used in more conditions.
Okay. Thank you.
Thank you. That will be it.
Okay, so opponent, please summarize.
So now to the concluding remarks. So first, we discussed the Worthington jet, but they had a clear description on how their theory would fit. Then we go to a graphing chart, which they have a clear chart because of the missing error bar. Then the direction of shock wave. They have wrong description. Only consider two directions. And then we discuss about the speed of the shock wave, and they fail to consider in their calculation. Then the contact angle of the ground. Well, they also fail to consider. Then we go to the visual representation of the experiment, which they kind of lack. And then we went to the vertical 2 liters of container, and they also lack of evidence.
reviewer.
Okay, first, I want to ask both of you about the experiment. What do you think is the main factor that caused the greatest height of the experiment? Okay, the main factor that is.
I think is the water value.
How about you?
We think it's the shape and the radius of the container.
Container. And I want to ask the reporter about how many times we did the experiment.
How many times? We do an experiment for 10 times, but we will
I mean, a
choose
total
the
time, aside from a whole experiment with the thing that is not accurate. The inaccurate data and accurate data. Or the same experiment, how many times?
what do you mean?
The total experiment times that you made for the same situation.
Same situation. 10
10 times?
Yeah.
Do you think that 10 times is enough for this?
But there are some just the manipulation that the container can go up, not vertically to the ground, horizontally.
Okay, thank you. What do you because you both mentioned that the ball may contact the container at the bottom.
Yeah.
What do you think is the ball will fall in fully in the water but not contact in the water?
Fall into the water.
The ball is all into the water.
Ball will sink all into the water. I don't think it will happen.
How about you?
Well, according to the graph the reporter had, the ball didn't completely sink into the water.
And then do you think it will happen if I have a longer container?
Well, I don't think the ball will fully sink into the water.
Okay. And what do you think the factors that form the jet?
Forming the jet. First is the magnetic space, and next is the velocity field that into this factor will make the jet happen.
For you?
Well, I think the factor from the jet will be the weight, but you have to consider the weight speed of weight from which direction would go to the ball before it launches.
Then the next question for the reporter. You mentioned that there is some difference that doesn't match your theory, but you said that the point is a little below because of the shock wave. But why isn't that okay, the other two things?
Other two things.
Okay,
you mean
answer.
I'm the reviewer from Team Overalls, and today I'm the review for the problem number 5, which is the ping pong rocket. And for problem statement, the ping pong ball is placed in a container of water. When the container is dropped, the ping pong ball will get launched to a very high maximum height can reach with up to 2 liters of the water. So the opponent and the reporter talk about the mechanism and how different diameters affect the maximum height. And for the overview of the reporter's presentation, in their observation and theory, they analyze the X and Y displacement and the free ball rebound, the Washington jet, and the momentum transfer to the mechanism and the air resistance. And their experiment method, they use a string and iron wire to control the ping pong ball and the bucket. And for their data analysis, the time scale of dropping is small enough that the height roughly moves to constant. And the drop height increased, the rebound height increased. And for their conclusion, when the container radius increase, it is the rebounding height increase. And 2 liters can reach to the maximum. And the pros and cons of the reporter, for pros, they have a clear demonstration of the phenomenon and organized results and data. They consider various variables. But for the cons, they lack of prediction of relation between the quantity. Is it linear or exponential? And they lack of experimental data and poor time management. And for the pros and cons of the opponent, they consider the iron wires effect and mention the air capsule and point out the missing point of the reporters. But the lack of suggestions of improvements. And for the discussion review, the opponent asks if the reporter observed the air capsule, and the reporter answered that there will be no capsule, but there are many spaces, and we think that there should be the air capsule. And the opponent asks why the data has no error bar, and the reporter answered that some error bars are smaller than the dots. And I think it may not happen because it should be a bigger range. And the opponent asks what is the shockwave direction, and the reporter answered that it should be vertically upwards. And we agreed to the opponent that the shockwave should be in all directions. And the opponent asks how do you keep the container drop vertically, and the reporter asks to use a straight strip. And I think that they should have more than 2 cameras to see, only not the x-axis, but for the 3 dimension, not only about the x-axis and the y-axis. And the opponent asks, did you consider shockwave in your theory? And the reporter said no, but I think it should be considered. And for our questions, I asked about what is the main factor of this phenomenon. And the reporter answered the volume of the water, and the opponent answered that it is the shape of the container. And we believe that the initial height is mainly the main factor without others, and maybe the volume will be the same. And we asked about if you think that the ball will sink through the water, and the reporter said it won't happen, and the opponent agreed with the report. And we think that it will sink into, the ball will sink into water in some moment, and when we have a larger container drop, and the velocity will be smaller with the container and bigger with the ball, because of the air pressure. Okay, that's all my presentation. Thank you.
Okay. So, reporter, please conclusion.
First, is that there will be a lot of deviation if we don't control the position of the ball in the middle of the container. And the shock wave generated by the container is only consists of the circular shocks and the shock wave perpendicular to the ground. And our experimental data has an arrow bar here, and we measured the outer the contact angle of the container, and we took the impact with the right angle horizontal to the ground to the account. Yeah, and next is our theory can consider the shape of the container using a continuity erosion, and we know the bottom shock wave speed by measuring the rebounding speed of the container. And there is no air capsule during the tsunami. This vacant space that is created by the temporary force that pull the ping pong ball under the water, and also the velocity field and create a jet. And we consider the wave in our theory. Yeah, that we will mention that I didn't consider the shock. Thank you.
Okay. So, any questions or comments?
Yes. Okay. You talked about Washington jet, which we were not very familiar with, but I guess the applicability of that theory must depend on that there exists vacant space in water, either in ping pong ball or under the ping pong ball. Is that what would you say? Is that the correct statement? There should be a vacant space below the water surface, including space of ping pong ball when it's submerged in water, or as the other two competitors insist insist you to answer this. There's void, empty space, under the ping pong ball, which you said you didn't observe any cut. Is this a presumption for using Washington jet? My question is that. Because if you use it, there should be some assumption. Is this one of them?
Assumption. We think
Or condition, whatever you call it. Because you just say you use the theory, but when can you use it?
we mentioned that vacancy.
Is it, no, just yes or no. You don't have to explain. I just want to know your answer. Yes or no? The other two could answer the same.
Any assumption?
You do not get my point. You use the Washington jet. When does that happen? It happens under what condition? Anytime you water in the bucket being dropped onto the ground, it happens?
Yeah.
Without ping pong ball and without anything?
Without it, you don't have the vacant space. So we don't
But your ping pong ball is a vacant space.
Yeah.
I'm
So
giving you
yeah.
hints, but you don't get it.
Yeah. Okay.
Your answer I got. How about the other two? You were the first to raise the question of Washington jet, which some say Washington jet. I was amazed yesterday. They don't know, but they use it.
The reporter thinks that in order to use
No. What's the condition for using the theory of Washington jet?
The reporter said there must be a vacancy space under the object that's launched.
But does the void space, the empty space of ping pong ball underwater counts? I just want to know.
Well,
Your opinion.
No, because the reporter didn't observe a vacant space under the.
No, the ping pong ball is a vacant space.
Oh, you mean the vacant space inside?
I don't think you.
Well,
you-
we think the vacant space in the ping pong ball doesn't count. It has to be the
How about
vacant
the,
space under the.
that's okay. How about the review?
I agree with the opponent that I
Okay.
think the vacant space don't be possible.
Okay.
Okay, please.
I have a basic physics question for 3 teams. Basic physics question. When a ping pong ball collides with the water, ping pong ball collides with water, does this process involve an elastic collision or inelastic collision? Please give a brief explanation for your answer. Who wants to answer first? Elastic or inelastic collision?
I think it's
Reporter.
elastic collision. We have the
Sorry?
inelastic.
Inelastic.
Inelastic. And we have experience. We use numbers to swap the water. And so we found that the rebounding flux is not the same.
Thank you. How about the reviewer or
Well, the
opponent?
opponent thinks that it's inelastic.
Inelastic
Because the
collision.
ball is colliding with a fluid, which the energy, some part of the energy might lost during the process.
How about reviewer?
We also think that it's inelastic because the kinetic energy is not consistent.
Thank you. Okay. So you can sit. Let's just take your scores.
物理模型应该想象出来吧？
Okay, so let's have the score. At first, reporter. Okay, 87787. Okay, it's quite average. And the opponent. And then 97767. Okay, well. And the reviewer. Okay, 76667. Okay. Good. Any comment?